In this lecture, we will talk about the wigner formulation of quantum mechanics. This is an alternative formulation which is not very popular. It is totally equivalent to the Schrödinger formulation of quantum mechanics, which is the standard formulation. So we will start from the Schrödinger one, and from that we will introduce the wigner formulation. This is not a course about quantum mechanics, so I expect that the audience is somehow familiar with the standard formulation. You are aware that quantum mechanics was born as a set of rules that were necessary for the explanation of very particular experiments which involved extremely small objects. One of the first milestones that was reached was the Schrödinger equation, which was actually the first equation that was general enough to be applied to a plethora of experiments, and which was successful enough to give correct predictions. Actually, the Schrödinger equation is not the full story. You actually need the Born rule for this. And this is why on the next slide we show it. So in the Schrödinger formulation, every quantum system, and I mean every experimental setting in a sense, are explained by means or are expressed or described by means of complex wave functions. You may imagine these wave functions as complex functions, which are defined on the configuration space. The configuration space here, we mean the space of coordinates or spatial coordinates of all particles involved in the experiments. Actually, even though we can describe system completely by means of wave functions, one should be careful and not attribute any kind of physical meaning to this function. This is just a mathematical function. There is no way in nature to measure actually a wave function. The only thing you can do with this wave function, and this is where we have the Born rule, which is a heuristic rule, is you take the wave function, you take the square of the modulus, and this gives you the probability of finding a particle in a particular position or in a particular area of the space or the domain you are studying. So this is the only thing you actually do in practice with the wave function. You calculate macroscopic variables, and the way you do it is by means of the Born rule, which tell you what's the probability of finding a particle. Observables in this formalism, in this formulation of quantum mechanics, are represented by operators, which is a very big departure from the Newtonian or classical mechanics, where your observables are actually numbers that you measure. So the correspondence between the mathematics and the experimental settings or the experimental measurements is straightforward, while in the Schrödinger formulation this connection is not simple anymore. You have observables, and what you do with these observables is to find an operator which represent this observable, and what you can do with these operators is you apply them to the wave function, and you have an eigen problem which tell you what are the possible outcomes of measuring that particular observables. So it's a very big departure from what usually is known in classical mechanics, and this is the way it works in the Schrödinger formulation. Another important point is that in the Schrödinger formulation you have two main equations that describe the dynamics of a wave function of a system. The first equation is the time-dependent Schrödinger equation, which is the first equation you see in the upper part of this slide. This is a time-dependent problem. This is an initial value problem. You define a wave function that describes the initial conditions of your experimental setting at a time, let's say t equals 0, and this equation tells you how the wave function will evolve in time. While if you are interested in the stationary solutions of a particular system, you solve the time-independent Schrödinger equation, which is an eigen problem. So there your unknown is still a wave function, but also the energy that is connected to this wave function. And as a matter of fact, what you have out of this, the resolution of this equation is a set of allowed energies, or in other words, you have the energetic spectrum. Other formalisms of quantum mechanics exist. Schrödinger is not the whole story in quantum mechanics. For example, another early development, an early formulation of quantum mechanics was given by Heisenberg, which is in terms of density matrices. Eventually, Paul Dirac showed that the Heisenberg and the Schrödinger formalisms are actually the same, let's say, are just different facets of the same theory. But you also have drastically different ways of describing quantum mechanics. For example, you have the Keldysh formulation, which is also known as non-equilibrium green formalism. It is also called like this because there your main unknown is the non-equilibrium green function. You also have the formulation which was given in the 50s by Feynman, which is the path integral method. You also have the Wigner formulation, which is the one we would focus on, which is given in terms of quasi-distribution functions. But you also have, for example, the Uzimi formulation, which is defined in terms of positive definite functions, which are very similar to distribution functions, and many others. So here what we want to do is to focus on the Wigner one, because we think that there are many advantages of focusing on this approach. In particular, the language is extremely close to whatever experimentalists are familiar with. The Wigner formulation was actually given in 1932 in a paper on the quantum correction for thermodynamic equilibrium. So you may understand that what Wigner was looking for was not really a second formulation of quantum mechanics. He was more rather interested in finding quantum corrections to the Boltzmann equation, which is the main equation in classical statistics or classical statistical mechanics. He ended up with the equation that you see here, and you can understand that this equation wasn't very popular at the beginning because of the mathematical tractability. As a matter of fact, this is an equation which is a partial integral differential equation, and this is an extremely difficult mathematical problem to solve, even if you want to tackle the problem from a numerical point of view. Your unknown here is a distribution function, or I should say a quasi-distribution function defined over a phase space, and this is a 6-dimensional space. And if you have more than one particle, let's say you have n particles, then this phase space becomes a 6 times n dimensional space. So you understand that mathematically speaking, this is a very complicated problem. But this is not the whole story. In the phase space formulation of quantum mechanics, or let's say the Wigner formulation, you have two main equations. The first one is this one we have been talking about, the time-dependent Wigner equation, where you start from a quasi-distribution function that describes the initial conditions of your system, and you calculate the evolution in time of this quasi-distribution function. While if you are interested in the stationary states of your system, what you do is to use the second equation you see in the lower part of this slide, where this is a Stargent problem. This star symbol that you see here is called also the Moyer product, and this is a quite complicated problem from a mathematical point of view. But in any case, these are the only two equations in the phase space formulation. If you are interested in time dependent, is the first one. If you are interested in the stationary solutions, is the second equation. So to go ahead, we may mention that these quasi-distribution functions despite they are used in this formulation as distribution functions. You use them as distribution functions when you want to calculate macroscopic variables, or in other words, variables that can be measured. You see that these are not properly distribution functions. Indeed, for example, here you can find two pictures of two different wigner functions, and you see that both of them have negative values. So strictly speaking, these are not distribution functions. There is a price to pay in this formulation, and the price is that you have negative values in distribution functions. So this is why we always refer to this as quasi-distribution and not just distribution. Now, the very interesting thing is that nowadays experimental techniques exist which allow the measurement of quasi-distribution functions. And as a matter of fact, not only you can measure these wigner functions, you can even find the negative peaks, which is something rather interesting, because there is no way to measure in an experiment a wave function, but there are ways to measure a wigner function. So this means that the language of the phase space or wigner formulation is extremely close, and it's strongly connected to experiments. And we shall remember that after all, physics is about experiments. So if we have a formulation that is close to experiments, this must give you some advantage for sure. So this is one of the strong motivation why we would like to use the wigner formulation. Now, another interesting point that I will just mention here, and the interested audience can go to the paper on the bottom of the slide here for the details. It's that actually the Wigner and the Schrödinger formulations are mathematically completely equivalent. As a matter of fact, you use this Wigner-Weil transform that is reported here on the slide, and you can start from a wave function and find the corresponding quasi-distribution function, and vice versa. This Wigner-Weil transform is demonstrated mathematically to be invertible. So this means that there is a one-to-one correspondence between the space of wave functions and the space of quasi-distribution functions, or I may say the space of allowed or physically meaningful quasi-distribution functions. So these two formulations are completely equivalent. This means that whatever prediction you do in the Schrödinger formulation, these predictions are exactly the same as the predictions you would have in the Wigner formulation. And this is a very important point. This means that even though we are dealing with the quantum mechanics that is formulated in a phase space and that is very close to experimental language, this is still quantum mechanics. This is not a quantum correction to a classical theory. And this is a very important point. And finally, I would like to mention the advantages of using this formulation. So we mentioned that this is a full quantum approach, but this is also a time-dependent approach. So you can see how actually experiments evolve in time, and this gives you a lot of hints if you are interested in studying novel experiments which are not really understood. It is an intuitive formalism, as we saw. As a matter of fact, we don't speak in terms of complex wave functions here, but we talk in terms of distribution functions, which can be measured. The other interesting things is that you can include inelastic effects. In particular, you can include phonon scattering to some level, and this is a very important deal because this means that you can simulate or you can calculate the properties of an experiment at room temperature. So you may, for example, see if you still have dominant quantum effects at room temperature. This is something that is hardly achievable in other formulations of quantum mechanics. The other important point is that you can include easily, I mean, it is natural in this language, general boundary conditions. This is an important point, especially if you want to apply this thing to, let's say, realistic experiments or realistic devices. And least but not last, or last but not least, I should say, we have Monte Carlo techniques nowadays which are very powerful and which allows you to simulate time-dependent Wigner equation in the single and many body frameworks, and you can achieve an extremely big parallelization, an extremely high level of parallelization, which is an important point, especially if you have parallel machines in your department. And this will conclude this first lecture. Thank you very much.